The following video is on limit laws. We want to try to find the value of a limit exactly. And so far the only techniques that we have involve plugging numbers in very close to C and then using our calculator to estimate, or using the graph of a limit to estimate. In this lesson we'll learn how to find them exactly using algebraic techniques. So to start off, let's start with some building blocks. The first building block is that the limit as x goes to c of the function y equals b is b for any constant b. To verify this, we can look at a graph of the function y equals b. Remember, that's just a horizontal line through the y value b. And no matter where we put c on the x-axis, as we get closer and closer to x equals c, the y value is going to be b. And that's simply because the y value is b everywhere. Therefore, the limit as x goes to c of b equals b. The next building block we have is the limit as x goes to c of x equals c. And again, we can verify this with a picture. Here we have the function y equals x, and no matter where we choose x equals c on our graph, we notice that the y value at that x value is getting closer and closer to c. So therefore, the limit as x goes to c of x equals c. For example, we can do the limit as x goes to 5 of the function 3 equals, and here we're using the first building block, and b in this case is 3, so the answer is 3. We can do another example. The limit as x goes to pi of x. Now we're using the second building block. So whatever we plug into the function, we get out the same thing. So the limit as x goes to pi of x is pi. Let the limit as x goes to c of f of x and the limit as x goes to c of g of x both exist. We will now construct a bunch of laws that we can use with our building blocks to evaluate more complicated limits. The first law is the sum law. It says that the limit as x goes to c of f of x plus g of x equals the limit as x goes to c of f of x plus the limit as x goes to c of g of x. In other words, the limit of the sum is the sum of the two limits. This rule also works for differences, so instead of addition we could use subtraction, and the same thing holds. The limit of the difference is the difference of the limits. We can also look at what's called the product law. This says the limit as x goes to c of f of x times g of x is the limit as x goes to c of f of x times the limit as x goes to c of g of x. In other words, the limit of the product is the product of the limits. Here we can look at the limit as x goes to c of a constant b times f of x, and that's going to equal b times the limit as x goes to c of f of x. So in other words, we can pull any constant out of the limit, as long as it doesn't have an x. For the next law, we have the limit as x goes to c of f of x to the bth power equals the limit as x goes to c of f of x, where the whole thing is raised to the bth power. And this will hold provided that the value that we end up with exists. So in other words, if b was 1/2, we would not want the limit as x goes to c of f of x to be a negative number, because then we would be taking the square root of a negative, which gives us an imaginary number. For the next law, we have the quotient law. That says that the limit as x goes to c of f of x over g of x equals the limit as x goes to c of f of x divided by the limit as x goes to c of g of x. And once again, we only need to be worried about the instances where we might be dividing by 0. So we have to put the stipulation provided that the limit as x goes to c of g of x does not equal 0. Finally, we have the composition law. It says the limit as x goes to c of f of g of x equals f of the limit as x goes to c of g of x. Once again, we have a stipulation provided that the limit as x goes to c of g of x is in the domain of f of x. In other words, we're not plugging something into f that is not defined. Let's do some examples using these laws. Let's look at the limit as x goes to 3 of x squared plus 5x minus 6. I'm going to use the laws and break this down very slowly, but once you get more comfortable, you'll be able to do this a lot faster. So the first step, I'm going to use the sum and difference rules to break this up into 3 separate limits. I'll have the limit as x goes to 3 of x squared plus the limit as x goes to 3 of 5x minus the limit as x goes to 3 of 6. Now I'm going to use the exponent law for the first term, the first limit. I'm going to use the constant multiple law for the second limit, and I'm going to leave the third one alone. So I end up with the limit as x goes to 3 of x quantity squared plus 5 times the limit as x goes to 3 of x minus the limit as x goes to 3 of 6. Now we've broken everything down so it's using only our building blocks. We know that the limit as x goes to 3 of x is 3, and the limit as x goes to 3 of 6 is 6. So we end up with 3 squared plus 5 times 3 minus 6, which comes out to 9 plus 15 minus 6, or 0. Recall that a polynomial p of x is any function that can be written as a sum or difference of terms of the form a times x to the n, where a is a real number and n is a non-negative integer. So, as a theorem, we get that if p of x is a polynomial, the limit as x goes to c of p of x equals p of c. In other words, we can just plug in the value x equals 3 in this problem above to get the value of the limit. This is called direct substitution. So what we've just shown is that direct substitution, plugging the number x equals 3 in for x in the function, will work for any polynomials. Direct substitution turns out to be a very useful tool, and it's thankfully very easy to use. It works unless we get any of the following. If we must divide by 0, if we must take an even root of a negative number, such as the square root of -1, or if we must plug in a value that's not in the domain of that function. For example, the natural log of 0. In any other case, though, direct substitution will work. We might as well just do it. For example, the limit as x goes to 3 of the square root of x minus 1 ends up to be, using direct substitution, square root of 3 minus 1, which is the square root of 2. For another example, the limit as x goes to 0 of sine x. Doing direct substitution, we have sine of 0, which ends up to be 0. For another example, the limit as x goes to 2 of x plus 2 over x plus 1. Using direct substitution, we get 2 plus 2 over 2 plus 1, which is 4/3. So anytime you don't have to divide by 0, take an even root of a negative number, or plug something into the domain that wouldn't normally exist, any other time we just use direct substitution, and it's very easy. Direct substitution sometimes will not work, however. This happens when we have something that's called an indeterminate form. If direct substitution gives us something of the following forms: 0 divided by 0, infinity divided by infinity, negative infinity divided by infinity, infinity divided by negative infinity, negative infinity divided by negative infinity, infinity minus infinity, 0 times plus or minus infinity, 0 to the 0, 1 to the infinity, or infinity to the 0. If we end up with any of those forms, we cannot use direct substitution. This means we need to use a different tool. We can't determine the solution in each of these cases using direct substitution. So we're going to develop in the next video what I like to call our limit toolbox. The analogy here is that if we're dealing with a nail, we can use a hammer, and in this case maybe direct substitution, and the hammer will do just fine to get the nail into the wood. However, not everything that you come across in the world is a nail. If we're trying to drive a screw into the piece of wood, we need a new tool. So with limits, we're going to use other tools besides direct substitution when we are unable to find the answer using only direct substitution.